Whilst lines of infinite length are very useful to mathematicians, they're very difficult to get through the door of your house. And so in the real world, we look at smaller pieces of an infinite length line, which we call line segments. Okay, so line segments. These are what non-mathematicians call lines, but they're a line with two endpoints. Okay, so here we have a line on our Cartesian grid, always useful for describing and exploring. Okay, and we're going to call one of the ends A, one of the ends B, giving us a line segment AB. Now, one of the very important things you need to do about lines, especially if you're thinking about carpentry and engineering, is cut the things in half, okay? Or, if not half, then in any ratio, so cutting into a thirds or quarters at an equal length. So, let's just try cutting it half first. So, to cut a line in half, we need to find the halfway point. Now, the halfway point has got a posh name. It's called the midpoint of a line segment. Okay? So we are going to look at how to find the midpoint of a line. Now, to do this, we first need to be able to describe the line segment itself. So, to describe it, we've used a Cartesian grid. So you should all be able to work out what the coordinates of the endpoints of the line segment AB are. So off you go. All right, let's see. So A, the x coordinate component of the coordinate is 1, and the y coordinate component of the coordinate is 1. So that's the line 1, 1, 1, 1. And then here's B, so its x component is 3, and its y component is 9. So hopefully you've got 3 and 9. So we know the endpoints. A is 1, 1, B is 3, 9. And we want to work out where the middle of line segment AB is. Now, think about what you'd do if you had a piece of wood in the real world and you were trying to work out what the middle of the piece is. What would you do? Get a tape measure halfway along, mark it. Yeah? And essentially, that's what we're going to do in maths. Okay? So, the key thing is to know how long AB is. So, we need to work out its length. Okay? Now, because it's on a Cartesian grid, AB is defined in two different directions. Okay? It's defined in the x direction, on the x-axis, and it's defined in the y direction, along the y-axis. So, instead of trying to work out how long AB is mathematically, which we will do later on, but is a bit more tricky, we are going to define AB in terms of its horizontal and its vertical aspects. Or in this respect, we're going to look at AB's x and AB y. So ABX is this bit, because it's AB's x aspect, or x direction, okay? And how long is that? Well, we can see how long it is, yeah? It is 3 take away 1, which is 2, okay? So 3 take away 1 is 2. So AB in its x aspect is 2 long, and for ABY, well, ABY, which is this bit, is 9 take away 1. 9 take away 1, which equals 8. Okay, so AB in its x aspect is 2 long, and ABY in its y aspect is 8 long. So we're looking to work out where the midpoint is of these lengths. Okay, so what's the midpoint of ABX? Well, ABX is 2. So halfway along 2, you just divide it by 2, don't we? So we have 2 divided by 2, so that's 1. And 8 divided by 2 for the y aspect is 4. So halfway along this line, segment AB, is 1 and 4 in the x and y aspects. Okay, so if we just draw this in, we can see it. So we're saying on the x aspect for A and B, we need to go 1 across because that's halfway along. So 1 along. Okay, so we'll draw that. And then for the y aspect, we need to go 4 along from here. So from here, we go up, because y is up, isn't it? We go 4, 1, 2, 3, 4 to here, and we come across here. And that gives us 2, 5. Okay, and 2, 5 is our midpoint. Okay, and you can see that. Yeah, if you've got a ruler and measured the length, we put an M there for midpoint. If you measure the length of A and M with your ruler and then measure the length M to B, they'd be the same. Okay. Now, how did we do that? So we need to look at turning the method we've just used into some sort of formula. So mathematically, what did we do in the last part? Well, we divided a line segment AB up into its x and its y values, didn't we? So we did that first. So we found out how long AB was in its x, and we found out how long AB was in its y. Then we divided it by 2 to find out what was halfway along the length for ABX and ABY. And then we added it to the start point, which is A. So we added halfway along AX, and then we did the same for the Y. We worked out what halfway along AB's Y component is, and we added that to what the Y value for A is. Okay? And that's the formula. Now, it's a bit horrible, but we can simplify it, okay? So, what this relies on first is that A is the leftmost coordinate, if you can have a leftmost coordinate. If they're vertically stacked, so they're on top of each other, it doesn't matter which one. Now, the reason you have to have A being the leftmost coordinate is that you use B, as you can see, A, you're going to add to get to the midpoint, are you? Because it's here, and the line's going that way. So you need to add, coming this way, to get to here. If it was B, which is the rightmost coordinate, if you add to this, you end up over here somewhere, but that's not part of the line. So B, the method would work, we'd have to take it away from B, because you're going this way, aren't you? You're going towards the negative. So that's why we use A and we add. So we can write this out a bit more easier method now. So AX plus. So how did we work out the x length of AB? Well, we did BX take away AX over 2. And similarly for Y, okay, we did BY minus AY over 2. All right. Now, to make sure, or to eliminate mistakes, when we're working out the difference, we need to understand that sometimes we may get it the wrong way around, and a difference doesn't have a sign. So I'm going to introduce something here to help you. That should never be negative or positive. It should never be negative, okay? Because lengths don't have a negative value. So what we can do is use this thing called a modulus function. Okay, and it looks like that, those two lines. And what it's basically saying is whatever the value is of the calculation inside those two lines, if there's a negative on it, discard it. Okay, similarly with the Y, okay, we want the modulus of the difference, okay, which looks like that. All right, and that's how you can work them out. So for instance, let's have a look now. We can use this method here. So we'll slip that up there. So we know what A is. A is 1, 1, and B is 3, 9. So what's the x value of A? Well, that's 1 plus, so the modulus of bx, so bx is 3, take away ax, which is 1, all over 2, comma, and the y value for A is 1 plus the modulus of by, so that's 9, take away 1, all over 2. Okay, so 1 plus 3 take away 1 is 2. Okay, the modulus of 2 is 2 because there's no sign on it, no negative. 2 divided by 2 is 1. And then similarly for this, 9 take away 1 is 8. The modulus of 8 is 8. 8 divided by 2 is 4. And then you get 2, 5, which is, as we know, our midpoint. So here we have that lovely complicated formula. You're thinking, ugh, I can't be bothered with this just to work out the midpoint. I'll just stick a ruler on it and measure along it, which you could do. However, if we analyze this formula, we can turn it into something that's really, really powerful. Now, at the moment, all it's doing is working out a midpoint, which is halfway along. But what happens if we want to divide it into, say, a ratio of 2 to 1, or 2 to 5, or 3 to 6? Okay, there are all sorts of ratios that we can divide a line segment into. The same way in the real world, we might want to chop up pieces of wire or wood or metal into different ratios, depending on what we're going to do with them. So it would be nice if we had a general formula. Okay, so we're going to look at this and see what we can do with it. So there's the starting point for x, okay, and we're working out its length in the x axes, yeah. But then we're dividing it by 2. Now the 2 is because we want the midpoint. We're splitting it in half. Now if we're going to come up with a general formula that splits it into any bit, we want to turn that into a letter, okay. So if we're going to talk about splitting things into ratios, so a ratio of 1 to 1 means we're splitting it into 2. So the proportion we want is a half, which is where the division by 2 comes from. So let's use the letter P. So if we use the letter P to represent the proportion we want, we can stick it there, okay? Because if P is a half times something is the same as dividing it by its 2, isn't it? So a half times something is the same as dividing something by 2. So we can now generalize this formula, by take away ay, and that's times by p as well, okay, and that's much easier where p equals the proportion. Okay, so let's try that out on a more useful example. So here we have a classic question. Either they draw the line out for you or they give you the 2 coordinates. You'd have to draw the line out yourself. Okay, and we need to find out the coordinate of point x when the line segment CD is split into a given ratio. Okay, now we know that we're trying to find a point along this line in a given ratio. So we're going to use the equation we derived, or the formula we derived yesterday, which is 4 point AB. Okay, so we're going to swap that. We're going to put CD. See if we've got CD. So we know the formula is the x component of the leftmost coordinate, which is C, plus the proportion, so how far along we're going as a fraction, of the modulus of the difference of the length of CD in the x-axis. So dx minus cx. And then for the y, it was the leftmost y plus, again, the proportion of, times the modulus, so no sign of the difference of the y's. Okay, oops, and that bracket sort of fell off a bit. Oops, where's it gone? There it is. Okay, and all we need to do now is work out what the values are. So we know C What's its coordinates? So negative 5, comma, negative 1. D is 4, comma, 5. And then we need the P, the proportion. So the ratio here is 2 to 1. So as a proportion, that's 2/3 to 1/3. So we want to be 2/3 of the way along. So P equals 2/3. And then we just stick our values into our formula. So the x value of C is negative 5 plus the proportion was 2/3. Okay, the modulus of, right, so dx, so that's 4, take away negative 5, because that's cx. Okay, and then cy is negative 1 plus p with 2/3, the modulus of the difference between the y's. So d, so that's 5, take away negative 1. And then we just got to work them all out. So negative 5 plus 2/3 times 9. 4 take away negative 5 is 9, comma, negative 1 plus, I'll stick that in brackets, 2/3. So 5 take away negative 1 is 6, so modulus is 6. Okay, so we have negative 5. So what's 2/3 of 9? That is indeed 6. Oops. And then negative 1, what's 2/3 of 6? That's 4. So negative 5 plus 6 is 1, and negative 1 plus 4 is 3. So the formula is telling us that x is at 1, 3. So let's see, let's draw it in. 1, 3. Is that where x is? So let's have a look. We can tell because that goes along 3 and that goes up 2. Along 3 up 2. Along 3 up 2. So 2 along 2's up, along 3's up 2, as opposed to 1 along 3 up 2. 2, 1. Okay, so we know that we can see the formula works for this, and it'll work for anything. As long as you can turn a ratio into proportion, which is a fraction of the length, this formula will allow you to work out any point in any ratio along a line segment. So as well as dividing lines up into segments, or line segments up into smaller segments, so midpoints for halves or thirds or 2/3 or 2/5 or all sorts of things, one of the other things we're often asked to do is find the length of a line segment. Okay, and that can often be for reasons of, again, engineering or construction, lots of associated activities. So how do we find the length, EF? Okay, now, one way to do it, you could take out a ruler, you could measure EF, and then you could measure one of the squares themselves, and assuming the squares going for the x-axis and the y-axis were in the same aspect ratio, same proportion, you might be able to use a scale factor. But again, you're measuring it, it would only ever be an estimate. But we have a way of measuring it or working out its length exactly. And the way to do that is to go back to what we did when we were trying to work out midpoints. When we worked out a midpoint, we had to work the length out, didn't we? But because we said at that point it was too difficult, we used the Cartesian grid context to work out the length in two parts. We worked out the length in the x-axis. So let's change the color. We worked out the length in the x-axis, so here, and we worked out the length in the y-axis, which was here. Okay, and we used that to be able to work out how it affected the coordinates, because there was an x component and a y component to the coordinate. Now in length, there isn't. Length's just one measure, isn't it? It's one number. But if you look at what I've just drawn, you should see something that will help you. So what have we just drawn? Yep, we've drawn a right-angled triangle. And one of the beauties of the Cartesian grid system is there's right-angled triangles all over the place, okay? Any diagonal line can have a right-angled triangle drawn on it because you're essentially drawing the difference in the y's, so dy here, over the difference in the x's, okay? Now, what else could we add if this is a triangle? Well, EF we don't know, do we? That's the unknown we're trying to work out, so let's call that. Actually, let's not call it x, let's call it A, because we've already got an x in the x-axis. What else do we know, though? Well, we know the length dx, don't we? Because it's just the difference between the x components for the two coordinates. So if the two coordinates here are, so what's E? -5 and 6. Oops. And F is 2, -3. So the difference in the x is between 2 and -5, so that's 7. Okay, and the difference in the y's is between 6 and -3, so that's 9. So if we take that outside here, we actually have a triangle, which is 9 and 7, and an unknown here, which we'll call A. And there's the right angle. Now, if you were given that problem, how would you work out what A is? Okay, am I hearing some Greek? Am I hearing some people shouting, Pythagoras? Yes. And that is one of the reasons why Pythagoras is such a valuable tool in our mathematical toolbox, because Pythagoras can be used all over the place. And here, because we can construct a right angle triangle, we can use it when we know two sides to work out the length of the third side. Now, Pythagoras, remember, is in a right angled triangle, so it only works in right angled triangles. The square, so when you square a number by multiplying it by itself, the square of the longest side, okay, which is called the hypotenuse, and it's always the side opposite the right angle. So the square of the hypotenuse is equal to the sum, so if you add them together, of the squares of the two shorter sides. Now that's the way I teach it, because it's irrelevant how you name a triangle. Lots of people will learn a squared equals b squared plus c squared, but they also might learn a squared plus b squared equals c squared. Or they might learn x squared plus y squared equals z squared. And what happens if you have triangles with p, q's and r's? The problem is, unless you really understand what's happening, the letters can actually cause you more problems than they help. But learning it this way means the letters are irrelevant. You've just got to find a right angle triangle. You can always work out the longest side, because it's opposite the right angle. You square that, and then you let equal the sum of the other squares, of the other two sides. So it's a much easier way to learn. So let's follow this through then. So in a right angle triangle, yep, tick, we got that. The square of the longest side. So the longest side in our right angle triangle here is A. So the square of A, hopefully you all know, is A squared, equals the sum of the squares of the two short sides. Well, one short side is 9, and the other short side is 7. So A squared equals, or what's that, 81 plus 49. So A squared equals 81, 90, 130. So A equals the square root of 130. Okay, and often you'll find Pythagoras, especially using exact measures, will generate surds, okay? And if you should hopefully remember, a surd is something expressed as a root, and it's an irrational number. But it doesn't matter, because you all know what root 130 is. You just don't have to work it out. So the length of this side is root 130. Okay, and that's how you work out the length of a line in if you can put it on a Cartesian grid. A more common question, and more use of distances is to work out the distance between 2 points. Now this can be on a 2D grid or a 3D grid if you're doing A-level, but it's the same process. The distance between 2 points is, so the shortest distance between 2 points is a straight line, so you're working out the length of the line. So they don't draw the line for you, you need to draw it in yourself, or at least work out what it will be. Obviously, you don't have to sketch this, because you can do this by working out what dy and dx is and putting them into the formula. So remember, where's 4, 2? Let's have a look. So if we're going to do it the old one, so 4, 2's there, and that's A. B is -1, 7, so B is up there. Okay, and then we've got a straight line here. Oops, well, it would be straight if I drew it straight. So, what we're doing is creating a right angle triangle, which is our differences in the x-axis and our difference in the y-axis. So this is the difference in the y-axis, because we're going in the y direction. So 7 take away 2 is 5, and the difference in the x-axis is this one, because this is the horizontal x direction, and that's 4 take away -1, which makes it 5. So we are going to say that if we say this is a, what do we call it, A. So using Pythagoras, the square of the long side equals the sum of the squares of the two other sides. Okay, so A squared equals 25 plus 25, which is 50. So A equals the square root of 50, which, if you know your surds, is root 25 times 2, which equals 5 root 2. Units, well, there are no units here. We don't normally put units, okay? And if it was a context question, had centimetres or anything like that, then we'd need to make sure that we made use of that. Now, you don't have to draw it. You can use the formula, which takes this and says for any points any points A, X, Y, and B, X, Y, the distance between them, so the distance between them is given by the square root of the square, so here's adding the squares, of, so dy, well, dx first, so that's the difference between the x's, so that's bx take away ax, and then the y difference in y here is by take away ay. So as you can see, if we fill that in, bx is -1, so -1 take away ax is 4 squared plus by, so b's y value is 7, take away a's y value, which is 2, and as you can see, you end up with the same thing. It just means you don't have to bother drawing it out. Okay, -1 take away 4 is -5, so -5 squared plus 7 take away 2 is 5 squared. So that's the square root of 25 plus 25, which gets us back there. Okay, so that's the formula. If you don't want to draw a triangle out, we'll try and work it out, the differences. And if you do want to draw it out, that's fine. You can just draw a sketch. You don't need to go the whole palaver and draw a massive Cartesian grid to do it. Okay, so here's a question. A triangle has vertices, there's 3 points, and then the question is classify it. Now, to classify something, it means describe it. So triangles, how do we describe triangles? Well, we know that we have different types of triangles. We have scalene. Okay, scalene. What the hell's a scalene triangle? Scalene. Scalene, 3 sides and 3 angles are all different. Okay, so that's one. We have a right angle. Has a right angle. Shockingly. We have isosceles, okay, two sides and two angles, same length, same value, I suppose, because you don't have angles, don't have lengths, and equilateral, 360-degree angles, three sides, same length. Okay, so that's the classification we're going to have to work out. Now, you'll notice there's sides and there's angles. Now, we've been doing lengths of sides, so it's fairly obvious that's what we're going to be doing. So, we need to work out the sides, or the lengths of the sides of the triangle, because if they're all different, it's a scaling. Right angle triangle will come back to two sides of the same length, it's isosceles, and the three sides of the same length, it's equilateral. Okay, remember an isosceles can be an equilateral, and sometimes a right angle triangle can be isosceles. Now, the right angle one's a bit trickier, because right angle triangles, it's all about the angle. So the question is, how do we work out whether something's an angle? And we do that by using the reverse version of the Pythagorean theorem. Because if you remember, Pythagoras states, in a right angle triangle, the square of the long side equals the sum of the square of the two short sides. So if we apply it backwards, we can say that if the sum of the squares of the two short sides equals the square of the large side, or the longer side, then it is a right angle triangle. Okay, so again, we'll use reverse Pythagoras, but we're still going to work out the length of the sides. Pythagoras. Okay, now if it helps you, you can draw a little sketch. Some people might like it. So there's 1, 1, that's A, 3, 4, 3 and 4 is B, and C is 6, 2, 6, 2, which is about there, C. So there we go. Whoops. Okay, now you could draw it. You could accurately draw it and you could measure them all out, but you wouldn't be allowed to do that in an exam and use it to justify your answers, okay? You can only use it to help you. So off we go. So let's see. So we need to find out lengths. Okay, so we have AB, AC, BC. And we know that to work out the length, it's the square root of the difference between the x's and the difference between the y's. So difference between A, so what have we got? A is 1, so we'll do the x's. 1 take away B is 3 squared, plus, then we'll do the difference of the y's, 1 and 4. 4 squared, okay. This one, AC, is 1 take away 6 squared plus, what have we got? 1 take away 6 squared, and then we'll do the y's, so 1 take away 1 squared, because they're both 1s, aren't they? Oh no, they're 2s, do. 1 take away 2 squared, okay, and then BC is BC, so 3 take away 6 squared for the x's, and 4 take away 2 squared for the y's. Okay, so we could use a calculator, or we could just leave them in third form, can't we? So 1 take away 3 is negative 2, negative 2 squared is 4, 1 take away 4 is negative 3, 4 plus 9 is root 13, so that's that. 1 take away 6 squared is, so that's 5, my negative 5, so that's 25. 1 take away 2 is 1, 1 squared is 1, so that's root 26. 3 take away 6 is negative 3, so that's 9. 4 take away 2 is 2, 4, so that's root 13. So there are our lengths. So we can see that AB and BC are equal, okay? So therefore, we'd have to write this, AB equals BC, brackets, root 13. Therefore, it is a isosceles triangle. Okay, so it can't be a scaling. It can't be equilateral because three sides of the different lengths. Okay, we've got two that are root 13, one root 26. It is isosceles, but can it be a right angle triangle? So there we need to just check, okay? So if it's a right angle triangle, okay, therefore Pythagoras is true. So the long side is AC. So is the square of the long side equal to the sum of the squares of the two short sides? So root 26 squared is 26. Root 13 squared is 13. Root 13 squared is 13. Is that 26 equal 13 plus 13? Yes. Therefore, it is a right angle triangle because Pythagoras is true for it. Okay, so that's an example of one sort of question you might be asked. But often, there's lots of reasons, questions that try and hide in them places where you need to work out lengths. Yeah, often triangles mixed up with straight line graphs, with circles, tangents and radii that you have to work out lengths of to be able to calculate things. Okay, so always keep an eye out for if you need a length and there's a Cartesian grid somewhere, you may be using this method. Okay.